Hello, and welcome to this session, LO3. Be able to design and implement simple state machines. In this session, we will explore a central question. Have you ever wondered how everyday devices like traffic lights or vending machines operate? These systems rely on a fundamental concept known as state machines. In this video, we will examine the principles behind state machines and guide you through their design and practical implementation. A state machine is a computational model used to design systems with distinct states. It transitions between these states based on inputs or events. Key components include states, transitions, inputs, and outputs. The initial state is where the system begins, and it may have a defined final state. State machines are crucial for managing system behavior. State machines are widely used in computer science, embedded systems, and robotics. They help in designing logic where outputs depend on input sequences and current states. Finite state machines, Mealy models, and Moore models are common types. State diagrams visually represent transitions and inputs. These principles form the foundation of state machine design. To design a state machine, first list all possible states. Next, define the inputs that trigger state changes. Create a state transition table or diagram to visualize transitions. Choose a programming language or tool for implementation. Coding involves using conditionals to simulate transitions between states. Consider a traffic light controller with states like red, green, and yellow. Transitions occur based on a timer input. In Python, conditionals handle these transitions. The system cycles through states in a defined sequence. This example illustrates a simple state machine in action. Python is a versatile language for implementing state machines. A traffic light state machine uses classes to define states and transitions. The transition method handles state changes. The run method simulates the state machine over multiple cycles. This approach demonstrates the practicality of Python for state machine design. A simple door lock FSM has states like locked and unlocked. Transitions depend on inputs like correct or wrong codes. The system returns to locked after a timeout. This FSM ensures secure access control. Such examples highlight the versatility of state machines in various applications. State machines find applications in user interfaces, game design, and embedded systems. They manage button states, character behavior, and control circuits. Protocol design uses FSMs for network communication. Digital electronics benefit from FSMs in microcontroller logic. Their structured approach ensures reliable system behavior. Testing state machines involves verifying performance and debugging. Edge case analysis ensures robustness. Digital tools like Python and Verilog aid in testing. Proper testing prevents potential system failures. This step is crucial for reliable state machine implementation. State diagrams visually represent system states and transitions. They model behaviors like process life cycles and user authentication. Diagrams help in understanding complex processing scenarios. They ensure every possible state and transition is considered. These visual tools are essential for effective system design. A process lifecycle diagram models behavior in a multitasking OS. States include new, ready, running, waiting, and terminated. Transitions occur through events like dispatch and timeout. This scenario illustrates state management in operating systems. Such diagrams aid in understanding complex system interactions. A user authentication system diagram includes states like start and authenticated. Transitions depend on events like entering credentials or failed attempts. Lockout occurs after multiple failures. This scenario highlights security considerations in authentication systems. Diagrams ensure all states and transitions are accounted for. A file read operation diagram includes states like idle and reading data. Transitions occur through events like disk readiness. This scenario models data retrieval from a disk. Diagrams help visualize the process flow. They ensure efficient handling of file operations. Programming languages like Python or C implement basic state machines. A turnstile FSM example includes states locked and unlocked. Transitions occur through events like inserting a coin. This approach demonstrates the practicality of programming for FSM design. It provides a foundation for more complex implementations. Logic design uses hardware tools like Verilog for FSM implementation. A simple FSM example includes states A and B transitions occur through input events. This approach suits real-world hardware applications. It complements programming methods for comprehensive FSM design. State machines offer simplicity and deterministic behavior. They ensure real-time efficiency and visual modeling. However, they face limitations like state explosion and rigid structure. Evaluating these aspects helps identify performance bottlenecks. Improvements address these challenges for better scalability. Enhancements like hierarchical state machines reduce state explosion. Event-driven models improve responsiveness. Object-oriented design enhances modularity. Domain-specific tools automate FSM design. These improvements enhance scalability and flexibility in complex systems. Traditional FSMs work well for systems like traffic lights. Game AI benefits from behavior trees or event-driven FSMs. Web browser navigation requires hierarchical FSMs. Embedded control systems may add hierarchical states. Evaluating use cases guides appropriate FSM enhancements. Tools like LOGISM and Quartus aid in FSM simulation. Programming languages offer flexibility for FSM design. Verilog and VHDL suit hardware implementations. Domain-specific tools automate and optimize FSM design. Choosing the right tool depends on the application and complexity. State machines manage systems through defined states and transitions. They are crucial for predictable behavior and structured design. Improvements enhance scalability in complex environments. Choosing enhancements depends on system requirements. State machines remain essential in both hardware and software applications. In conclusion, we have seen that enhancements play a crucial role in increasing both the scalability and flexibility of complex systems, enabling them to adapt more efficiently to evolving demands. We appreciate your attention. Should you have any questions, please contact UKversity via WhatsApp at 07484 361,688. Thank you, and we look forward to seeing you in the next session.